Good morning. Welcome to Al Shifa Online TV with me, Dalila Hamza. Today being a Monday, let's sharpen our witty. And we have our teacher for today is Mr. Muhammad, who'll be taking us through mathematics. I know it's your favorite. And remember that the show is sponsored by Al Shifa Muslim Youth Initiative in conjunction with Al Shifa Online TV, together with Radio Salam, Mombasa, Kenya, and the Office of the Senate of Mombasa, Brother Muhammad Faki. I hope you enjoy because our witties are going to be activated.
Welcome on board. I hope it's a fine Monday and everybody is healthy enough to enjoy the lesson, our lesson for today, whereby we'll be introducing a new topic on logarithms, whereby our last topic where we stopped, we had already finalized on surds. Today we'll be handling on logarithms. Okay, first of all, it's good to share with you the objectives of the lesson, that by the end of the lesson you should be able to define logarithmic notation from index form and vice versa, state laws of logarithm, and third, use logarithms to simplify logarithmic expression and solve logarithmic equation. So first of all, before we proceed with the logarithms, it's very important to remind ourselves on the indices. Okay, when we ask ourselves what are indices, these are numbers which are written, or expressions which are written. For example, 8 can be expressed in the form of 2 power 3, which is equivalent to 8. So we call this 2 as the base. Then 3 is the exponent. Whereby in indices also we have, for example, you are asked to show how does it come to be an 8 can be expressed in the form of 2 multiplied by 2 multiplied by 2. So when you are told to express 8 in the form of indices, you are only asked to express it in the form of 2 power 3. As well as, for example, you are asked to express 9 in the form of indices, is the same as 3 multiplied by 3, which is equivalent to 3 squared, and so forth. For example, the number 12, when expressed in the form of indices, is equivalent to 2 multiplied by 2 multiplied by 3, which is equivalent to 2 squared multiplied by 3. So these are indices representations of numbers, whereby in the laws of indices we have that when numbers of the same base multiply, we have 1. We had laws of indices. We have, if it is, for example, a power m multiplied by a power n is equivalent. When the bases are the same and they are multiplying, you add the powers. So it's equivalent to a power m plus n. Whereby second, we have that when the bases are the same, a power m divided by a power n is equivalent to a power m over a power n, which is equivalent to a. Then the power will be subtracting a minus n. Then thirdly, we have that when given a power m power n is equivalent to a m multiplied by n. So having these ones in mind, it will become easy for you when we enter into logarithms. For example, we have 2 power 3 multiplied by 2 power 2. We are told to simplify. This will be equivalent to 3 plus 2, which is equal to 2 power 5. You can leave it up to that, or you can simplify it further by getting the value. But if you are told to leave it in indices form, you just leave it as it is. When you ask 3 power 4 divided by 3 power 2, this will be equivalent to 3 power 4 over 3 power 2, which equals to 4 minus 2, which is equal to 3 power 2. You can leave it that. If you are asked to leave it in index form, you just leave it like that, or if you are told to find the exact value, this is equals to 9. That's a quick review on indices. Then we'll see that indices relate to logarithm, because given an index form of a number, you can change it into logarithm. You're told if y is equal to a power x, then we introduce the inverse function. Logarithm and define. So y is equal to a power x. We'll get log y is equal to a power x, which is equal to x log a. So getting x to be the x will be equivalent to log y to the base log a, which can be written that log x is equal to log y to the base a. We'll say that when given an equation in index form, you can change it into logarithmic notation. So This is our base, this is the exponent, and this is the value, the number. So by practicing much, the conversion of index form to logarithmic notation and vice versa, logarithmic to index form, will become very easy. But if you fail to practice, it may be tiresome or even hard for you. Quickly, let's look into the logarithmic laws of logarithm. So we find that y is equal to a power x implies that log the base y is equal to x. This is the conversion of index to logarithmic notation and logarithmic to index notation. For example, we have log 10 to base 10 is equal to 1. You can see if it is correct by changing it to a logarithmic index form, whereby this is the base times the exponent you'll get. So this becomes 10 power 1 is equal to 1, and we see that it is correct. So mostly in our 4-figure table, the logarithmic notation or logarithmic values we get are to the base 10. So in most cases it can be written as log 10, log to the base 10 of the number, or at times it can also be written as log 10. When no base is indicated, you should have in mind that it is to the base 10. Unless otherwise, if the base is not indicated, have in mind that it's always to the base 10. the laws of logarithm are as follows. We have the product and the quotient laws, whereby log of numbers which are multiplying is equivalent to the log. Addition is equivalent log to the base a of m times n is equivalent to log of m to the base a added to log of n to the base a. Then when the numbers are dividing, log to the base a of n m over n is equivalent to the log of a base to the base a of m subtract log to the base a of n. Then the power laws of logarithm, you have that log to the base a of m to the exponent n is equivalent to n multiplied by the log to the base a of m. We'll look into some example to see how it is being done. So in our question here we have log to the base 6 of 9 added to log base 6 of 8, subtract from them log to the base 6 of 2. So we go back to the laws of logarithm, whereby when the logs add, so it means the values multiply. This will be equivalent to log the base 6 into bracket 9 multiplied by 8, subtract log to the base 6 of 2, which is equal to log to the base 6 72 minus log the base 6 2. So this gives us log the base 6 72 over 2, which is equal to log the base 6 36. When you divide, you get 36. So up to there, we have now to find the log. We can say is equal to x, then we change it into the index form, whereby it will be 6 power x is equal to 36, and it's equivalent to 6 power x is equal to 6 squared. So in this representation, it gives us that x is equal to 2. Let's see another example. 5, as I mentioned earlier, that when the log has no indication of the base, it means it is the base 10. So there's no difference when it's written like log the base 10, 5. This is equivalent to log 5. When no indication of log is written, you should have in mind always that it is to the base 10. So here we'll be applying the power laws of logarithm, whereby this is equivalent to log 5 squared plus log 2 squared. So this will be log 25 plus log 4. So is equal to log. Since the log add, the values will be multiplying. And here we'll get log 10. So we'll have to get the value of the log. Since it is the base 10, you can indicate that is equal to x, then it will be 10 power x is equal to 100. And we know that 100 is equivalent to 10 power x is equal to 10 squared. So from that representation, we'll get that x is equal to 2. Then you have logarithm of roots. You have that log to the base b of x 1 over n is equivalent to 1 over n log the base b of x. Here we know that when a number is, for example, a when it's written like that, it means a power, but when represented root to the root b, this can be also represented as a to the power 1 over b. So this can also be equivalent to log the base b to the root n of x, or log b of x over n. Then we'll try to prove some of the properties, the laws of logarithm. We have that log for example, when given log of b to the base b is equal to 1. Proving it, we try to change it into the index form, whereby we'll have that b, this one, to power 1 is equal to b. So we see that it corresponds to that property. Then we have, second we have log b1 equal to 0, which when changed into the index form, we'll see that a number to the base, to the exponent 0 is equal to 1, which is equivalent to this property. Then you have log xy is equal to log bx plus log y to the base b. Then we say let log the base b of x is equal to m and log of y to the base b is equal to n. So when you represent them in the form of index representation, here we'll have b power m is equal to x. And here we have b power n is equal to y. So x multiplied by y is equal to b power m multiplied by b power n, whereby x is equal to x multiplied by y is equal to b m plus n. xy is equal to m plus n log b. So it's equal to a log xy over log b, which is equal to m plus n. So this representation is the same as log xy to the base b. So it means that you find the log of xy to the base b. So that's why we get log xy to the base b is equal to m plus n. Up to here we have seen on how to go about how to convert index form into logarithmic notation and logarithmic notation into index form. And also we have gone through into the logarithmic notation. So in our next session, we'll be looking into how to solving exponential and logarithmic equation using the logarithmic laws. So we'll be putting into practice more. We'll be putting more practice into the logarithmic notation and see how we can manipulate them during solving the logarithmic equations and exponentials.
Well, I hope you enjoyed the lesson, though we come to the end of the lesson, but not the day. We're going to take a commercial break, but we'll be right back with more fascinating lessons for you.